Okay, welcome back. And this video is for the marine transportation folks among us, or anyone that is used to thinking in terms of navigation. And I wanted to show the correspondence between what we've been talking about in physics, these relative velocities in inertial reference frames, in other words, things that are moving with relatively constant velocity rather than things that are accelerating, which makes things a little bit more difficult. And I wanted to show the correspondence between the two fields to show how physics kind of worms its way into the rest of your curriculum, current and in the future. So in navigational language, course steered and speed through water. So it looks like this and this around the line that you draw to represent the magnitude and direction of what is a vector. That gives the direction and magnitude of velocity of a ship relative to the water. In our terms, that's V sub SW, right? Velocity of ship relative to water. And that would be the apparent speed of the ship, right? You point the ship in a certain direction, you undergo a certain number of turns per minute on your propeller, and you expect to make a certain amount of headway if there is no current in that direction and in that speed. But of course, there tends to be current. And that, as you probably already know from your navigation courses, is referred to in the following way. So currents, which is the velocity of water relative to the Earth, is the direction of it is given by the set, and the magnitude given by the drift. And in terms of physics, in our language here, that's the velocity of water relative to the Earth. So the velocity of the water relative to the Earth, okay, WE. Now, I've drawn them in this way because, one, this is one of the sort of standard triangles that you see in navigation, okay? There's a few different ones depending on what information you have and what you're looking for, okay? But also, okay, to show you that this triangle, when you complete it, corresponds to this vector sum that we've been talking about. And if we put it in the appropriate pattern, we can know that the two velocities on the right sum to give us the velocity on the left. So velocity of the ship relative to the Earth. So ship relative to the Earth, so VSE here, has a magnitude and direction given by speed made good and track made good, respectively. And that appears in an identical triangle, assuming you're doing everything to scale in terms of the length of these lines to the magnitude of those vectors and their directions. That triangle and that triangle should look exactly the same if you're doing a good job drawing them. The only difference is being that, well, I know these aren't supposed to be solid circles. I guess they're supposed to be open in navigation, okay? But otherwise, a really similar thing. Okay? Here we use arrows to make sure we know which direction we're going. Here you're sort of reliant on the degrees, right, in each one of these things to tell you sort of which direction that line is, whether it's sort of up this way or down that way, for instance, okay? But we know that this pattern where we have a first subscript appear here, and then the subscript that does not appear on the left here, so W in this case, is sandwiched, so to speak, on this side by that first S and that second E, right? And that vector sum, okay, and we know from the graphical method in physics that if you start at the origin and you plot out what the velocity of the ship relative to the water is, so its apparent velocity, and what the velocity of the water relative to the Earth, so the current is, then we just need to attach the origin to the head of that second vector to get the sum of this vector and this vector. So the right-hand side of that equation equaling the ship's true velocity relative to the Earth, okay? Now, I'm going to set up an example. I pulled it directly from Bowditch that will illustrate one more time sort of the correspondence between the navigation problem that you might be doing and the equivalent physics problem. And the only real difference between the example out of boundage and what I'm going to write out here is that I've translated the headings, so the directions, out of navigation land and into physics land, right? Because in navigation, you start at 0 at north and you count up going clockwise. And in physics and engineering and math, you start, well, on the equivalent of east and count up degrees going counterclockwise. Not a big change, but one worth remembering. Okay, so you desire to, say, make good a course. So want course made good and speed made good of 185 degrees and 15 knots. Okay. And we know that the estimated current is 3 knots. So its drift is 3 knots. And with a set of 265 degrees. Okay. Now we want to achieve this, okay, and to figure out what the ship's heading and the apparent speed of the ship should be, we need to apply what we know about vectors. First, let's translate the given quantities and what we're trying to find in this problem into physics language. So the course made good and the speed made good, that's the true, quote-unquote, true velocity of the ship. And that's the ship's velocity relative to the Earth, not the water around it. And that's going to be 15 knots. We're free to use that unit if we want at 185. We just don't want to mix knots with like meters per second or something crazy like that, okay? Use all the same unit and you're fine. And then we also know that the water is moving relative to the Earth, so the current at 3 knots with a set of 265. Okay, and the thing that we're trying to find is what apparent speed and course must we maintain such that we get the result on the first line. So the velocity of the ship relative to the water is what we want to know so that we can do that and achieve the first line. Okay? Now, I'm going to draw this out. I'm not going to go through the whole 2D vector problem because you're pretty familiar with those at this point. But let me draw an origin here, and we'll sort of take and put in some axes. So there's your north-south axis. There's your east-west. And let's just plot out our 2 vectors, which are both attached to the origin, which is sort of standard practice for physics. Not so much for navigation, but we are in physics class. So the first one, the velocity of the ship relative to the Earth that we desire, 15 knots at 185 degrees. So that's just below the axis. So let's say it's gonna look something like this. It's probably more than 5 degrees, but we'll stick with it. And that's the velocity of the ship relative to the Earth. And then we've got a much smaller vector, right? The current that is at 265 degrees. So that is like, right, something along those lines, okay? The velocity of the water relative to the Earth, okay, at 265. Now, how do we combine these 2 vectors to figure out what we need, okay? Well, we can put it into that equation. You can also do the navigation thing, but let's see how it corresponds to physics. We know that that first subscript has to appear there. The first one on the right is the first one on the left, and vice versa. And we sum that with, we have to sandwich the e's right here and here. And then the second subscript has to be that W because it's the second subscript on the left, okay? Now we don't have this vector, right? We have that vector, but with the subscripts reversed, though. And so we can rewrite this with a negative and flip the subscripts, right? We can always do that. If we want to just flip the subscripts to fit it into our pattern, or because it's more convenient, all we need to do is take the negative of that vector. So the sum of v sub se and negative v sub we is going to give us the thing that we want. Okay, so we know what the negative of a vector looks like when we plot it out. It just looks like the same vector, but rotated by 180 degrees. So there's negative VWE. Here's, I can draw it freehand, or relatively freehand. And so I'll try to just move it down here to the head of VSE and keep its orientation, yeah, something like that. Not quite. I think I made it a little bit too long. Okay, but pretty close. Okay, so we take that, we put it to the head of VSE, and that means that if we want the sum of those two things, right, which is going to give us this answer here, we need to connect the origin to the head of that second vector, just like that. That's going to be the velocity of the ship relative to the water that we have to direct the ship to do, so that we actually get this 15 knots at 185 degrees. Okay? So this graphical method, and also what you would be doing in navigation, albeit without the arrows and plotting it slightly differently, okay? But the basic idea remains, okay, that from knowing two velocities, you can figure out a third. And no matter which bit of information you're looking for in these triangles, you can always get that to go if you're using the appropriate method. And from what I understand, you'll actually, down the road in advanced navigation, sort of do out these kind of problems where, like we do them in physics, where we're finding the components thereof and summing up the x's and summing up the y's, and finding the total, in this case, this one on the left-hand side of the equation. Okay? So I hope seeing this example and some of the correspondence in the terminology of physics and the terminology of navigation has been helpful to you, and I'll see you later.